Thank you so much for watching this online video tutorial. Like, comment, and share, as well as subscribe to our channel at Good Better Best Online Videos for more video content. Right, grade 11s, we're busy today with the kinetic theory of gases. Okay, now the kinetic theory, okay, of matter. Okay, let's just talk about matter for a second quickly. We all know that matter is anything that takes up space. All right, it's a physical quantity. All right, or it's a physical thing that takes up space. You know, so and matter exists in three forms: solid, liquid, and gas. Right, and now of course we are busy with the third phase of matter, which of course is gases. Okay, so the kinetic theory of matter, it does explain the behavior of gases as follows. Number one, the first theory that it tries to explain is that gases are made of particles. Okay, if your teacher at school has done a demonstration before on the three phases of matter, they'll put a solid in a big syringe, they'll put a liquid in a big syringe, and they'll put a gas, which is normally just air, in a big syringe. And of course they will show you which can be compressed and which cannot. Okay, so we will obviously see that liquid and solid could be any type of solid, powder, rocks. I know my practical was rocks, just little stones from outside all chucked into the big syringe. Solid can't be compressed, a liquid can't be compressed, and but a gas can be compressed. Okay, gases, they are made of particles. Okay, but these particles, they are very small in comparison. Okay, let's just get this part down. They are very small in comparison to the space between them. All right, and this means exactly what I just said, that they are compressible. Okay, that's the first one. All right, the second one is that forces between the particles are weak. All right, they are weak, however, except during a collision. Okay, particles collide, then the forces between them are a bit stronger. Okay, now the weak forces in a gas, they allow the gas particles to be in a state of constant high-speed random motion. Okay, as a result, all right, of these high-speed random motion, okay, the gases undergo diffusion and always fill the whole container in which they are placed. All right, so we can summarize that due to high-speed random motion, gases, let's find a better way, always fill Alright, let's see the room. Or fill the entire container in which they are placed. Okay, that goes without saying. Let's just see if I can fit another theory in here. I think I can fit maybe one more. Okay, there we go. Now, as a result, okay, of that, the volume of a gas thus results from the motion of its particles, not from the volume of actual particles. Okay, something very important here on this note, that the volume of a gas, okay, is equal to, all right, the motion of the particles The motion of particles and not the actual gas particles. So in other words, they are not counted. There could be 500 of them. So just for example, there is 500 gas particles in a container. The volume of that gas is not 500. No, it's their motion. The motion of those particles, because they are random and they fill the entire container, that is rather what determines the volume of the gas itself. Now, because the whole container is filled by the gas, the volume of the gas is taken as the volume of the container in which it is placed. Okay, so if the volume of a certain container is 3 let me just see, a 3 liter container, then the volume of the gas would also be equivalent to 3 liters. Okay, any of us have a gas tank? Okay, maybe for a gas stove, or maybe you guys have a gas heater, maybe. Then the volume of gas that would be there when you go fill up your gas tank, you usually request the exact amount of kilograms or volume or mass of your gas tank. I have a 9 kilogram gas tank, a fairly big one. Most people rock with a 5 or 4, but I have a 9 kg, so it's fairly big. Lots of gas can be filled in there. Alright, so I always go and I say fill up the gas tank, and I walk out with 9 kilograms of actual gas. Okay, that obviously is now working out the mass and not volume of the gas, but I'm sure with a quick calculation I possibly could work out how much volume of gas is in a 9 kilogram gas tank, but that's for another day. All right, let's see what else we got here. Okay, gas particles, they do collide elastically with one another. Okay, with the sides of the container. So what does that mean when I say they collide elastically? That means that no kinetic energy, all right, which is energy due to motion of an object, in this case the gas particle, no kinetic energy is lost. Okay, it's lost during the collision. Okay, during the collisions, the particles exert a force on the container, or on the sides of the container rather, and that results in pressure. Okay, so let's try and summarize that point. Okay, gas particles collide elastically. Okay, elastically. There we go. Almost spelled it wrong. Which means no, and I'm going to say EK, which is kinetic energy. No EK is lost, and because they exert a force on the container sides, all right, on the sides of the container, they therefore also exert a pressure. Okay. Let's see if we can somehow fit that in here. We got to be able to somewhere. Let's see. Let's see if we can fit it in here. Give me a moment. Circulation particles. Let's see. Particles colliding on sides of container, using some shorthand text here, equals pressure exerted on container. Yes, a little bit of a tight squeeze here, but we made it. Awesome. Right, ladies and gentlemen, the fifth one is that the particles of a gas, they do not move at the same speed. Okay, let's denote that. Particles in a gas do not move at the same speed. So now, what does this mean? If they don't all move at the same speed, then that means that they won't have the same amount of kinetic energy. Alright? So they do not have the same kinetic energy. Okay. Another note over here about that, okay, is that the average kinetic energy of the particles determines the temperature of the gas. So, to make that point a little bit more summarized and more direct, the temperature of a gas is determined by the average kinetic energy, which I'm going to shorten to the average EK, alright, of the particles, or of the gas particles. There was a scientist in the 1600s that was called Robert Boyle. Okay, one of the few scientists that we have a look at today in our curriculum, which names that is quite easy to pronounce. But he did investigate a mathematical relationship between pressure of a gas as well as gas volume. And this investigation allowed him to basically state that he has obviously discovered something, hence the law would be named after him, which we have today called Boyles Law. Now, what does Boyles Law state? Okay, firstly, he measured what I just mentioned, volume versus pressure, okay, of a gas. Okay, volume versus pressure of a gas we can obviously have a look at with a graph. Okay, but before we get there, let's first have a look at the definition. Okay, Boyle's law states the volume of an enclosed gas is inversely proportional to its pressure, provided that the temperature remains constant. Like I said in my introduction, Boyle's law has got nothing to do with temperature as a variable, but it does require temperature to be kept constant, because if that is not kept constant, we cannot accurately measure the relationship between volume and pressure. Okay, so mathematically what we are saying is that volume versus pressure, okay, we find that there's an inverse proportional mathematical relationship between the volume and the pressure. So if I have a little bit of a graph here, okay, there we go, and I have pressure, volume on the y-axis and pressure on the x-axis, you'll see that the graph will look something like this. Okay, obviously I would draw it much better on paper as what I would be drawing it here on a virtual tab. Okay, so mathematically we're saying that volume is, let me write a bit of V there, volume is inversely proportional to 1 over P, okay, 1 over P, that's the mathematical relationship, which also basically means that therefore volume is equal to K times 1 over P. Now what is K equal to in this regard? K is a constant. Okay, K is a constant, which is the value, all right, on the quantity of the enclosed gas. Okay, if volume is inversely proportional to pressure, okay, if it's inversely proportional to pressure, okay, then basically we can also demonstrate this relationship as well. In other words, take that if volume is inversely proportional to pressure, this can also be read that volume is actually directly proportional to 1 over pressure. In other words, if pressure was 500, all right, then volume would be directly proportional to 1 over 500. Okay, taking the pressure and inverting it to make it 1 over pressure instead of pressure over 1. Okay, and that graph would obviously look something like this. Okay, so if we had 1 over the pressure on the x-axis and V over here, the graph would be a direct relationship, as opposed to the volume is inversely proportional, meaning that as the volume increases, pressure decreases, and as the volume decreases, pressure increases. Okay, both can be read, could be read in that way. Okay. Oh, got out of the window there. Sorry. Cool. So, either way, it's fine. Okay. The formula, which I'm just going to put on this side. Sometimes, for Boyles Law, they might give you a graph that has exact this relationship here. 1 over the pressure. Okay. So in order for you to determine pressure, you will need to obviously invert, right? Do your conversion here. Okay. The formula for Boyles Law, all right, is pressure P1 times V1 is equal to the pressure of the second gas times the volume of the second gas. All right, so we're comparing two different pressures of two different volumes of two different gases with each other. Okay, or we could be comparing a decrease in one and an increase in the other, trying to find out what is the missing variable. Okay, which I'm going to put through an example in just a moment. The example that I put there in the group, we're just going to go through. The volume of air in a balloon is 2 decimeters cubed. Please take note of what volume and pressure and everything is measured in. Okay, volume should be measured in decimeters cubed, and pressure can either be measured in pascals or kilopascals. So 80 kilopascals is basically 80,000 pascals. So in the question, the volume of air in a balloon is 2 decimeters cubed at a pressure of 80 kilopascals. At what pressure will the balloon burst if the maximum volume of air that it could contain is 5 decimeters cubed? So what I'm going to do is, for the purpose of the recording, I'm going to say that the volume of air, which is the gas in this case, P1, is going to equal to 80 kilopascals. Okay, and it said that V1 of that air was 2 decimeters cubed. And then they ask, at what pressure will the balloon burst if the maximum volume of air that it can contain is 5 decimeters cubed? So the second volume that I got there was 5 decimeters cubed, and the second pressure is what they want me to find out, which would be the maximum pressure, or the pressure that the balloon will actually burst. So what are we going to use here? Okay, we use Boyles Law, and we know that because they've only measured, or mentioned rather, pressure and volume. Okay, so let's use it. For the solution, green. P1 V1 is equal to P2 V2. So we have 18 multiplied by 2. Okay, go check, times P2, which is unknown, times 5. Okay, so I end up with 160 is equal to 5 P2, divide both sides by 5. Okay, now if I am correct, which I am, therefore the second pressure, which will be the maximum pressure, all right, or the pressure that the balloon will burst at, is equal to 32. And because we use the kilopascal value here, we have to say kilopascals, right, which is 32,000 pascals. Okay, so we can write as a conclusion the balloon, that's balloon, I've got to write it properly, give me a moment. The balloon will burst at a pressure above or more than 32 kilopascals. So anything more than 32 kilopascals, it'll burst, okay? Because 5 decimeters cubed is the maximum volume it can hold, so it can only hold a maximum of 5 decimeters cubed at a pressure of 32. Anything above 32 with that volume, the balloon is gone. Okay, it will burst. Okay. And that, grade 11s, is Boyles Law essentially in a nutshell. Thank you so much for joining me on Kinetic Theory of Gases, where we looked at Boyles Law in this session today.